Good morning, ladies and gentlemen. Welcome to this one-day symposium for the light science and its applications. The United Nations, for some unknown reason, which I don't understand, proclaimed the year 2015 to be the year of light, which is certainly a delightful surprise for someone working with photons. But anyway, for whatever reasons, I think they do the right thing time to time, and this is something that they do right. And so today's one-day rather informal symposium is basically to pre-celebrate this light, the year of the light, and we are really very honored and happy to have two distinguished scientists, Professor Marvin Cohen and Professor Ron Shen, who have made very important contributions to science of light, and they make use of light to understand the property of materials. It is in fact quite amazing if you look at the problem from the physics point of view, because light interact with material sometimes in a very complex manner. It's very, very difficult to disentangle the information and make some sense out of the data and understand the details. So this morning we are very happy to have two pioneers to tell us from both a historical perspective and also help us look into the future to see how light can help us understand the properties of matter. And in the afternoon, then we will move on to the other side of the coin. We will look a bit at the applications of light, how we can use light to see beyond the diffraction limit. And the textbook tells us that if you use light, you can not resolve image to better than half a lambda. But Professor Loy is going to tell us that no, with modern technology, you can see much better than that. And Professor Aaron Ho from Chinese U is going to tell us how we can use optical methods to do optical sensing. Obviously, is going to have very important implications for healthcare. And Professor K.W. Che is going to tell us how we can crank up the power of laser to make things non-linear, and then they are open in a whole new field of possible applications. So without further ado, I would ask the head of our physics department, Professor Michael Loy. I'm sorry. Professor Michael. Mike, I'm used to it. Professor Michael Altman to chair the morning session. Now, I have to say something which is rather unusual. Usually, the organizer will tell the session chairman is that, sir, please help us to keep us on time. But we purposely make the program scheduling quite relaxed. And the whole purpose of this kind of occasion is not a kind of high-power information exchange. I just want to tell you that I've done this, you don't try. Okay, I've done that already. Not that kind of thing. We want people, all of us, to have more opportunities for discussion. So I have just did the reverse and asked the chairman to go easy. Okay. Do not tell the speaker to shut up and do not cut off the questions. So we want to allow for more interaction. And also one thing, in the after lunch, in the afternoon, we are going to move to the 4th floor seminar room. Okay. So without further ado, let me invite Professor Michael Altman.
Former head of the Department of Physics. I'll tell Nancy about the change. Okay, so it's a great honor to introduce this morning's two speakers, esteemed visiting professors to the IAS and HKUST, and going nothing more than just the titles. I think this looks like a condensed matter morning, but please correct me in your talks if I'm wrong. So please, without any further ado, Professor Marvin Cohen from HKUST IAS, Berkeley.
Well, thank you very much for inviting me and for the introduction. Ron Shen and I were talking about what we were going to talk about. And I guess it's, in a sense, everything I'll be talking about will be linear optics, and he'll do probably linear and nonlinear. And we had the impression we were going to talk to students mostly. So I see some more senior people here. And so I have to tell you that you're going to be hearing something that you probably have heard a lot of before. And I tell a story which maybe I said here before. When I was running a colloquium at Berkeley, I invited Felix Bloch from Stanford to come to Berkeley to give a talk. And Felix said, but I spoke there 2 years ago. I said, that's okay. We'd like to hear you talk. So he came and he got up and he said that he apologizes to the people who are going to be hearing things again that he had talked about. But he said his good friend Heinrich Casimir once told him, never underestimate the value of hearing something twice. So I went to a conference in Europe that following summer, and I had just given a colloquium at Berkeley, and some of my Berkeley colleagues were there and other people. So I told the story of what Felix Bloch said, and I said, so I'm going to be talking about some things that you've heard before. And after my colloquium, this man comes up to me who I'd never seen before, and he says, I'm Casimir, I never said that. And then he started grilling me on the theory of superconductivity. So again, I'll try to give you some feeling for how far we've come, and also try to convince you that a lot of the reason that we've come this far in understanding condensed matter systems, solids, is because of the early work on the optical properties. Now, at the beginning in studies of solids, people looked at their mechanical properties, hardness. And in fact, in the 1800s, there was this MOHS scale of hardness where you scratch one thing with another, and the more you, the one that scratches the other one is considered harder. And then, of course, as we learned more about doing analysis, solids were classified according to what chemicals they were made out of. And then after that, X-rays came along, and that was very important because you could look at crystal structures. But you could get two solids with the similar crystal structures, and they can have very different properties. So the most important experiment, I think, in terms of classifying solids was the resistivity. So if you went around the world and took everything and measured its resistance and converted to resistivity, you would find that you have a parameter that has a very wide range, something of the order of 10 to the 35th. And we're all familiar with the fact that copper has a resistivity of 10 to the minus 8 centimeters, while quartz is 10 to the 17. So in everyday life, you see this. And the question is, how do you explain this? And how do you explain the fact that solids seem to group? You have metals, which have very low resistance, semi-metals, which are a little peculiar, and there are not a lot of them, but they're in between, and then semiconductors. And as you know, depending on their doping, they can go from, let's say, 10 to the minus 4 to 10 to the 11th ohm meters. And then we have insulators that can really inhibit the flow of electricity, diamond being an example. And essentially, the grouping was explained, and the concepts involved were fairly simple once people knew quantum mechanics. Because if you take a box and fill it with electrons, then you're going to get energy levels. And because of the Pauli principle, you're going to put 2 electrons in each state. And if the system has a gap, so that the filled states, you fill all the states, this is 2 electrons per cell, and then there's an empty state, then if the electrons have to jump the gap to give you conductivity, then if it's a small gap, it's a semiconductor. If it's a big gap, it's an insulator. And if it's no gap, it could be a metal or a semi-metal. And if you shine light on so this has enough energy, you can pull the electron right out of the crystal. So this essentially explained what was going on, but it didn't give you the details of what was happening. And in particular, when you give an explanation of the resistivities, it's just in terms of the states very near the fundamental band gap or near the Fermi energy. But most of the properties of the solid require a knowledge of the electronic structure over a wider energy range. And this is obtained by studying optical spectra. And you try to look at the optical spectra that, where the structure is coming from electronic energy level transitions. Now, if you go back on the theory of condensed matter, Einstein did a lot of work on condensed matter physics. In fact, well, he had many thesis proposals, and I gave a talk here once about how they were all refused by his very knowledgeable professors. Thermoelectric effects, heat conductivity, condensation of gases, intermolecular forces. And fortunately, they let him have a thesis on the sizes of sugar molecules. And that was very important because at the time, there were a lot of people who needed to be convinced that atoms exist and that you put them together for solids. And of course, he got his Nobel Prize for the photoelectric effect. And then Dirac and others were involved in the development of quantum mechanics, and that made a huge difference. Einstein also, through the photoelectric effect, said some very important things about quantum theory. And then Sommerfeld beta, and of course Dirac and Fermi developed statistical mechanics so that you could deal with electrons. So let me go through a little bit, but I thought one of the first condensed matter papers that many people are familiar with is Einstein's calculation of the specific heat of diamond. Now, we teach our students that it wasn't quite right down here because it was fixed by Debye, because low temperature, you're exciting acoustic phonons, and so this should go as the third power, but it's an amazing fit, and it's still in textbooks today, and we're talking about, 105 years or something like that, and very few of the papers written by people nowadays are going to be around 105 years from now, but it's pretty impressive. But the quantum theory that went into thinking about oscillators really developed, and so that by 1929, Dirac was able to make this challenge. He basically said that the underlying physical laws necessary for a large part of physics, and maybe all of physics, I mean, nobody has found anything, as far as I know, that shows that quantum theory is wrong, and all of chemistry are known, and the difficulty is sort of solving those equations. Solving the equations connected with quantum theory to explain properties. But quantum theory itself was basically developed because people saw funny things in the optical properties of atoms. So you're looking at optical properties of gases, and of course Planck's observation of the quanta in thermal properties and so forth. So optical properties were essential in establishing quantum theory, and quantum theory was essential in establishing the structure of the atom, the electronic structure of the atom. But for solid-state spectra, it was hard to do because, as Chi-Ting said at the beginning, unraveling the spectra is very difficult, and mostly because they're very, very broad. So here are the sodium D lines, and you can see how sharp they are for atomic spectra. Here's some other atomic lines. If you compare that with a solid, you'll see in a moment that it's much sharper. So here's the traditional transitions between the ground state and these two excited states, and the difference is 21 millivolts. So people analyzed atoms very carefully. That helped to prove the quantum theory was right. And the quantum theory helped to prove that the theory of atomic structure was right. But here's a typical reflectivity curve as a function of energy taken by Cardona and his collaborators who worked on many semiconductors. And notice here we're going from 6 volts to 20 volts. And this is the kind of structure you would see in a solid, where the atomic lines are probably the thickness of this line is what the atomic lines are like. So it's very difficult to say that you can understand solids by looking at optical properties of this kind. Fortunately, things got better. Here's another example of you could actually maybe get something like spin orbit coupling here because this is a mercury compound, so it has a big spin orbit coupling, but it was very hard to interpret. So people looked at it, but they didn't quite focus on atomic spectra and solids from this point of view. They certainly were aware of it and worked on it. The idea was to think about what happens for ideal cases, a box of electrons, a box of ions moving and so forth. And in 1933, Sommerfeld and Bethe wrote a review article of solid-state physics. And if you go back and look at that article, which is phenomenal in the sense that it reads just like an undergraduate solid-state text. In fact, it was Cattell who wrote a very famous undergraduate solid-state text who first told me about reading the article, and I think he read the article before he wrote his book. And if you look at the level, it was really very impressive at that time. However, these were general things about electrons and phonons and vibrations and crystal structures, and they didn't get to the stage where you could do materials science. And from the 1940s to the 1960s, people started developing methods to try to understand the electronic structure of solids, real solids. In other words, give you the name of a material and then you talk about interpreting its optical properties and you say something about its electronic structure. And it really wasn't successful. And in fact, even in 1957, when many advances were being made in condensed matter physics, such as the theory of superconductivity, the Bardeen-Cooper-Schrieffer theory of superconductivity, which was one of the great theoretical triumphs in our field of the last century, there was still no accurate, detailed knowledge of the silicon band structure. People really didn't understand the details. And we know how important silicon is. We use it every day with our computers and devices and all the rest. And it was Conyers Herring at a meeting of the American Physical Society who got up and said that we all think that we've known this forever, but it was not until recent years, I mean, this talk was given maybe in the 70s or 80s, that we actually got to understand the electronic properties of solids. And the major focus that helped do this was optical properties. Because by 1965, it was possible for us to calculate 14 important semiconductors using an empirical approach, empirical pseudopotential method, very, very accurately. In the 1970s, the physics of the optical structure of semiconductors was solved for the visible and ultraviolet. I'll show you more. In the 1980s, there were successful calculations of the structural properties of solids, and that led to explaining and predicting superconducting properties, surface properties, high pressure properties. All this became available because of the analysis of optical properties using empirical approaches, and then going to ab initio approaches where you don't need experimental input. And then in the 1990s, all the way till today, this developed into methods for doing calculations for complex materials, for nanostructures, and for a variety of properties of materials. And I claim this all rests on the analysis of optical data. And things got a lot better. because you saw how broad the spectra were before, but then a man by the name of Serafin decided to look at modulated spectroscopy, and then others came in and did it much better. And one of them is Ron Shen, who's here. So here is same kind of optical spectra as you saw before, but now instead of plotting the energy spectrum as a function of reflectivity as a function of energy, Ron and his group looked at the modulated reflectivity, the change of the reflectivity with energy divided by the reflectivity. And he was able to get this dashed line, which gave you the reflectivity over a range of, let's say, 6 volts here. Now, with theory, because of this empirical pseudopotential approach, with 3 parameters, which I'll tell you about, you can reproduce this entire curve. And remember, these are detailed transitions between energy bands. Every one of these peaks is a transition, and they're different structures. And the reason for the difference in theory and experiment here is that the theory doesn't put in exciton effects. When you take an electron from an occupied state and put it into the empty state, you have an electron in a hole. And the electron in the hole can then, positive and negative, they can bind together, or they can almost bind together, and that enhances. So these things were taken care of later. In addition, actually, this is one of Ron Shen's students, T. Chang, several people developed this technique of photoemission spectroscopy. A la Einstein, you shine light in, electrons pop out. But people thought mostly in the old days about just the photoelectric effect where electrons from a metal would pop out of the metal and you could get conductivity from those electrons. But now, the experimentalists were able to look at the electrons and look at, with an analyzer, they could see the energies of the electrons, and they could actually plot out the band structure, the electronic band structure, the energy as a function of momentum. Now, up to this point, no experiment was done that actually got a band structure directly. They got interband transitions, they got various properties through the optical properties that told you what, if you could unravel it, you could find out what the band structure meant. But here, they could actually plot energy as a function of momentum in different directions in the Brillouin zone. And before that, theorists used to talk about these curves back then in dark rooms, and they all knew what the Greek letters meant, and it was like a secret cult. But they never thought the experimentalists would come out and actually measure it, and then they did. Some of the pioneers here were Dean Eastman at IBM and Bill Spicer, who was at Stanford, and so forth. So that changed things. And so that one could start thinking about the idea of what did we do? How did we get to this point? And how did these optical studies and photoemission studies help us? Well, it's clear that if you're going to make a solid, you're going to make it out of atoms. And there are 2 popular models, standard models of a solid. And I'll tell you about both of them. The first one, very successful, interacting atoms model. Start off with a gas, and this was one of the things Einstein wanted to work on for a thesis, but his thesis advisor wouldn't let him. And then look at how the interactions develop into a liquid, and then as you lower the temperature or put pressure on, eventually freezes into a solid. So you start with atoms, and then the atoms interact very strongly and give you a solid, and you have electronic properties of that solid, which came from the atom, but they can look very different. Now, you know that the particles that went in, you know that that all you have are electrons and cores. And the core is the nucleus plus the core electrons. And then the valence electrons are in between. And you know that the only interactions that are important are electromagnetic interactions. The strong interaction is too short range, gravity's too weak, weak interactions are too weak, they're too short range. So you have electromagnetic interactions, you know the particles, and so perhaps some of our particle theory people would say, problem solved. But you have 10 to the 23rd particles per cubic centimeter. And amazing things can happen when you have systems of that kind, even if you know the particles and you know the interactions. So the kind of model that, that we use is, for this interacting atoms model, is you take the cores and you put them in a periodic array like this, and you assume that the core electrons don't change when you build your solid. And it's only the valence electrons that move around. So this is a schematic model of a covalent semiconductor like silicon. But none of the covalent semiconductors ever crystallize in the simple cubic lattice, so it's schematic. And the valence electrons, if you do a minimum energy, you'll find that they concentrate in bonds. So if this were silicon, the nucleus would be plus 14. The valence electrons, 10 valence electrons, would cancel and screen it. So now you get a plus 4 core, and the 4 valence electrons per atom go out and form these bonds. Now the question is, how do those electrons interact with the core? Now it's obvious that the core is positive, the electrons are negative, so you're going to get a potential. So the Coulomb interaction, this is a function of R, is going to be 1 over R. But when they get near the core, because of the Pauli principle, the electrons, the valence electrons, get pushed out of the core because they can't occupy core states. So this is like a Pauli force that pushes electrons out. And you find that electrons will sit here in this bond region, and you just saw the picture where they concentrate at that point of the bond. So in interpreting Professor Shen's data, what we need to do is take this potential, put it in, calculate the electronic structure, and then calculate the reflectivity, and then the modulated reflectivity. And the easiest way to do it is to just take a Fourier transform of this. And if you take a Fourier transform of 1 over R, you get something like this, except when you get to big Q, this would be the wavelength or Q vector, it starts coming down because you've got the core. And because it's in a periodic crystal, you only need the potential at these reciprocal lattice points. So in fact, that's why I could represent that whole potential if I put it into silicon or germanium. That was a germanium curve from Ron Shen's group. All I needed was 3 parameters. And I knew that the potential is to look something like this, so I can guess it quite easily for a first approximation. So in the old days, we just guessed that parameter, put it in. This is a structure factor that puts all the atoms in the right place, solve Schrodinger's equation, calculate the reflectivity, the derivative of the reflectivity, the density of states to compare with photoemission, compare with experiment. If it's not quite right, change the V of G and go back. And those electronic band structures that you end up with, for example, here's germanium, based on data of the kind that you saw, the accuracy has never been exceeded in any of the calculations, even with modern calculations. So empirical approaches, which are, let's say, favored by the more senior people like me and other senior people that I work with, and frowned upon by younger people like some of you back there, they want first principles on everything, can be very useful in telling you what's going on physically. And then you can develop, go further and develop ab initio. So for example, the experiment here, remember, was optical properties. So how can it tell you something about the bonding? Well, once you do the optical properties, and you have the electronic structure, then you get a wave function. You can square the wave function, and you can tell where the electrons are. And that can tell you something about the bonding. So here, for example, in silicon, here are the two cores, the positive cores. And these are like contour maps. They're contour maps of electron charge density. And you can see that it peaks halfway between the two silicon atoms, is for silicon. So that egg-shaped kind of ball of charge was the first picture of the covalent bond in a material. And I remember I was at Berkeley and John Wheeler came through and he gave a talk on general relativity and black holes and so forth. And he said, and we're in an era where we don't even know what the covalent bond looks like. And so I took him up to my office and I said, that's what it looks like. And it's like that TED production on education where the teacher tells all the children to draw pictures. And then she walks over and there's a little girl drawing a picture, but she's going slowly. And the teacher says, well, what are you drawing? And the little girl says, I'm drawing a picture of God. And the teacher said, but no one knows what God looks like. And she says, they will in a few minutes. So the nice thing about this is that it came before the experiment. And it showed that you could actually calculate bonding properties by knowing the optical properties. And it was, again, a big advantage in having optical properties done with high degree of accuracy. Now, essentially, by going back and forth between experiment and theory, it was a wonderful era because it was a very close collaboration. The optical properties originating from these interband transitions were essentially explained. And the theoretical work was based on the empirical approach. And the empirical approach focused a lot on the fundamental problems and set the stage for the development of ab initio methods. The ab initio methods were developed so that you would not need experiment. You could start just from knowing something about atoms and go forward. But the empirical approach also lets you do very empirical things because, again, connecting up optical properties with structural properties was quite exciting. For example, in 1812, MOHS had this hardness scale. And this was the scratch thing that I started out talking about. And he said that diamond was a perfect 10. And there's no ratio of physical constants that gives you a perfect 10 for diamond. So you are free to actually try to think of something harder than diamond. And it's not like the speed of light. And quartz would be here and so forth. Well, it turns out if you look at the optical properties, you can make a very empirical theory for the bulk modulus of a solid. That's the inverse of the compressibility. It can tell how much you can squeeze a solid, again, based on electronic structure and optical properties. And you find that you can argue that the bulk modulus should just be this simple, where the bond length is the distance between the two atoms. And this would be for the group 4, diamond, silicon, germanium, tin, and so forth. And then you can also use the theory to add an ionic factor because the charge, instead of being in the middle, will move over to the more attractive ion. And you get a simple formula for the bulk modulus. Again, it depends on the bond length to the 3.5 power. This is for 4-fold coordinate systems. But for the 3,5 semiconductors and the 2,6 semiconductors, the parameter of 1 and 2 is all you need. And the results are amazing. Again, these empirical theories tell you a lot about what's really going on. So here are the 3,5 semiconductors. Here are the 2,6 semiconductors. These are very important for applications. Here's the distance between, from the lattice constants, just the distance between the two atoms. Here's the experimental bulk modulus, and here's a calculated bulk modulus. And they're extremely good agreement. And even though now you can calculate these things from first principles, they don't come out as well as the empirical. So the idea at that point was that you had a theory and you could extend it in the ab initio direction, but you wanted a reason for extending in the ab initio direction because it worked very well. And the major reason was that when you built your crystal, the surface of the crystal was the same as the bulk because it was just the potential. And you know that at a surface, electrons rearrange because the bonds are cut. So you need to separate the ionic pseudopotential coming from the core and the electronic contribution. The empirical approach included everything together. So you needed a method for calculating surface states and calculating the potential. So for surface states, this is an old slide because this was at the time when this was developed. Since we were able to calculate crystals, and not so easy to calculate the end of a crystal, we built a supercrystal where you made slabs of materials and then made a cell out of the slab. And then in the cell, this would be your crystal, you would treat it normally, and this would be vacuum. So by doing an infinite number of these systems, this supercell approach, you could then look at what the surface looked like. And if you did that for, let's say, again, silicon, you'd end up that inside the crystal, there's that bond that's between the two silicon atoms. But when you allowed the electrons to move around and rearrange, they smoothed out. Instead of having a bond sticking out like this, and instead of having it cut in half, the charge rearranged. And you found there were channels that were going into the crystal, so impurities, that's how impurities get into the crystal. And then you could do surface physics by building a cell. Now, how do you make that ab initio potential? Well, you go back to Fermi. And again, it was optical properties. In the 1930s, Amaldi and Segre were looking at atoms like sodium and the alkali atoms, and they would excite electrons to very high orbits. And there were such high orbits that when they went around, they didn't really feel all the oscillations near the core. So Fermi said here, in Italian, but look, I don't need to know all these wiggles of a wave function near the core. All I really need to know is this part. So he extrapolated, this is r times the wave function, back, and in this remarkable paper, he invented the scattering length, and he invented the pseudopotential because he built a potential that would just reproduce this part of the spectrum. So to make an ab initio potential, you just take an all-electron wave function for silicon, and you build a potential that gives you exactly the wave function, but you forget the oscillations in the core and you just come back. And that's the pseudopotential. These are the modern pseudopotentials, and there's many of them, and they have them for every atom in the periodic table and even beyond the periodic table. So when they come up with new elements, you got your potential. You can go calculate that one of these unstable materials that last for a very small fraction of a second will be a metal if they ever make a solid out of it. So you can do all these hypothetical calculations. And so now you have a system where you could calculate things. The total structural energy is the energy of the cores interacting with each other, the electrons interacting with the core, that's a pseudopotential, kinetic energy of the electrons, the electron-electron Coulomb interaction, and then the electron-electron interaction, depending on density, the exchange and correlation. And you could use density functional theory to calculate these things. And that's the way most of the modern calculations are done. And so, for example, this was one of the early calculations where you calculate the total energy of a solid as a function of its volume, and you put it in different crystal structures. You can try any crystal structure. So silicon exists in the diamond crystal structure. So if you normalize the volume to 1 being the diamond, you find out this point determines what the lowest energy determines this point, and it gives you the lattice constant. And if you take the curvature of this, you get the bulk modulus. And if you reduce the lattice constant, put it under pressure, silicon goes into a beta tin phase, which is a metal. And the slope of this line tells you the transition pressure. And all these structures up here were predicted. And the only input is the atomic number to develop the pseudopotential and the structures that you're testing. And the kinds of results you get, again, only input atomic number in the crystal structure is you get the lattice constant to, less than 1%. Germanium's bulk modulus has always been a problem for some reason. Silicon, everything else is usually about 1%. So from first principles, you could calculate the properties. And again, you can now go back and calculate where the density is. And then, because diamond was such an interesting material, because it's so hard, there were many studies on what the bond looks like in diamond compared to silicon. And it's quite interesting because in silicon, the charge piles up in the middle. But in diamond, because there's no p state in the core, it doesn't push the charge, the p levels out. So diamond actually has a double hump bond, and that's why you're alive. The old story is that silicon is geology and carbon is biology. And the point is that because of this unusual structure of the bond, diamond can form multiple bonds. And then you can get a carbon biology, which you can't do with silicon. And this structure also allows you to have carbon go into an sp2 structure, and I'll talk about that in a minute, so that you can make graphene and graphite. And you can't make this under ordinary conditions. You certainly can't do it for silicon. You have to pull on silicon. So the thing is, I'm talking about optical properties, and that's what got us to this point. But if you use density functional theory, which is the usual theory that people use for calculating ground state properties, it won't tell you excited state properties. And fortunately, many body corrections to the density functional theory, a lot of them done by Stephen Louie, who is my colleague at Berkeley, could take these local density approximation estimates of the gap. This is the theoretical gap versus the experimental gap. The theoretical gaps were always too small because the density functional theory was not created for doing quasi-particles for excited states. And now with many body effects, you can get the whole thing. So now you can calculate not only the structural properties, but you can, for a broad class of solids, you can calculate clusters, molecules, and the electronic structure, crystal structures, and even electron lattice interactions and superconductivity. So I thought I'd give 3 quick applications. First, photovoltaics, and second, a little bit on nanostructure, and third, on superconductivity. And again, emphasizing the idea that optical properties are important. Now, one idea, and I think it's being adopted more now, is that people have thought about making semiconductor materials match the solar spectrum. So they talk about band gap engineering. They want the electronic band gap to be right to absorb light from the solar spectrum. But I would contend that wave function engineering is much more important, and that you have to think about this. And I'm going to show an example for structural phases of silicon. And also this will tell something about high pressure phases. So as I mentioned, The original structure, original calculations we did, we looked at silicon in the diamond structure, and the beta structure was known, beta tin structure was known. And then if you go up to the beta tin structure, you can actually come back and get another structure called BC8. Now, that was discovered, but the experimentalists didn't know how they got it. They basically said under certain heating conditions and cooling conditions, they could get these other structures. But we could tell that there are paths that if you go to one structure, you can get to another structure sometimes. And all these other structures were discovered that you could calculate with theory. And so this went on and on and on. And I'm going to give you an example of, sometimes people call this R8, sometimes they call it silicon 12. And it has a different property. Now, as I mentioned, with band gap engineering, let's say you want a band gap, this red line. And so you alloy semiconductors, or you put pressure on, you do different things, and you try to get something that matches the band gap. But that doesn't necessarily mean that you're going to get the right absorption. And what you want to do is you want to have a semiconductor so that when you vary things like alloying and the rest, that the absorption goes up. And I'll show you what I mean. Here is the solar flux as a function of energy. And if you take silicon and you look at its absorption, you see the band gaps down here are 1.1 volt, and the peak is here, but there's not much absorption. But if you put silicon under pressure and you make one of these silicon 12s or one of those, modified silicon changes the optical properties significantly. And you can actually get more absorption, and in fact, you can calculate the optical spectrum from first principles. If you just used, this is the imaginary part of the dielectric function, which is related to the reflectivity. If you just did this as a function of energy and you calculated using ordinary density functional theory, it just doesn't fit. But if you include all these electron-hole interactions and the rest, you can do it quite well. That's just to convince you that you can now calculate these things. So what happens is the absorption as a function of energy, eventually, if you go to a thick enough sample, even cubic silicon will give you enough absorption. But for thin samples, silicon 12, even down to, this is a log scale, even down to fairly thin samples, you can get a lot of absorption. So that's just an example of what you can do as a function of thickness and some of the applications if you use these kinds of theories. Now, a few words about nanostructures and a little bit about superconductivity, and then I'll end. The question, first of all, was whether or not these methods would work for systems that were not three-dimensional. For example, if you look at diamond in the chemical language has sp3 orbitals, and every carbon atom is fourfold coordinated. And the bond length is 1.54 angstroms. But the bonds in graphene, and this is a picture of graphite, where we have layers of graphene, these bonds are really short. So the bulk modulus, if you remember the formula, is even stronger. If you pull graphene this way, it's stronger than diamond in terms of whatever stronger means. It's got certainly harder to pull. But there are layers of these, and they're separated by an interplanar distance of 3.4 angstroms. And this interplanar distance, these things are held together by van der Waals interactions. So here you have this unusual strong covalent bond. Here you have a very weak van der Waals interaction between them. And that's why when you write with a pencil, the graphene levels, the graphene sheets come off. Or when you put Scotch tape on graphite, you can remove it and get a Nobel Prize. So the idea was you could then explain sp2 bonding, and so if you roll the graphene sheets into carbon nanotubes, you should be able to calculate it. And the methods work very, very well. So for example, if you take a hexagonal graphene sheet and you roll it around and you go around 8 units and you get something like this. And you can prove that that's a semiconductor. If you roll it around and you go 7 units and then slip up one, in other words, you go around and then you move the hexagons so that they don't match, you end up with a metal. And you can show theoretically that you can stick these two together if instead of having 2 6-fold rings here, you have a 5-fold and a 5-fold and a 7-fold defect. So here you have a metal, here you have a metal, here you have a semiconductor, there's a defect, and so this turns out to be a Jockey barrier, metal semiconductor interface. And experimentally, these were found and shown to be Jockey barriers. So in principle, you can do electronics on a much different scale. Also, using the theory, which now works from sp3 to sp2, it was possible to predict that you could have a tube that was even more interesting in many ways than the carbon nanotube, a boron nitride nanotube, where you replace, instead of carbon atoms, you have a boron and a nitrogen, boron, nitrogen all the way through. And the reason that this is so interesting is that it's a semiconductor. Actually, it's got a big gap, almost 5 volts, so you could say it's an insulator. But if you dope it, you can get electrons to be doped into the conduction band, and their wave function is right up the center of the tube. You basically have a tube that will have electrons coming all the way through. And there are many applications of this. For example, if you put an electric field on, you can make the gap smaller and so forth. But the main thing is that you couldn't make this material very easily. There were only a few places in the world, and now there are new techniques, and you can make a lot of it. And so, and it comes out, first of all, a boron nitride sheet is called white graphene instead of black graphene. It has some really interesting properties. And then in the tubes, they end up in stuff like this, and you can dye them, and they make clothes out of them, and you can use them for biology experiments. It turns out they're much more bio-friendly than the carbon nanotubes. So this area, and particularly a lot of work on boron nitride, is going to be very active in the next few years. Okay, the last part is I wanted to talk about elementary excitations, emergence, and superconductivity. I said that there were 2 models of a solid, the interacting atoms model and the elementary excitation model. And we saw that treating a solid as atoms that have come together and perturbed each other is a very good model. But the elementary excitation model is a completely different philosophy. So for example, if you do an experiment, somehow you probe a system. And if you're an experimentalist, then what you do is you measure a response function. So if you are a heat capacity person, your probe is to change the temperature, and then you measure the heat capacity. That's your response. If you're an optics experimentalist, you shine light on the system. The electromagnetic wave is your probe, and then your response function could be reflectivity, transmission, absorption, but you can get them all from the dielectric function, the real and imaginary part of the dielectric function, mostly. Now, the ideal machine I was told for an optical experimentalist is a box with 2 dials. One, you dial the frequency, and the other one, you dial the intensity. And if you could do it over the whole range from 0 to infinity or whatever, you could figure out everything in the universe. But you have to interpret what's going on. And that's where the response function comes in. So the probes are getting better and better. You're going to hear about lasers and things. They're getting better and better. And the response is a question of what, as I mentioned, whether you measure reflectivity or whatever. So the question is, how do you explain what's going on? Well, one way is to say that that box has a bunch of atoms in it. They interact. I get the energy bands. I look at the transitions. I get the reflectivity. But the point is that since what you know physically is only the response function, you can make up some ideas of what explains it in terms of the excitations of the solid. You just think of it as a box of elementary excitations. And you'd be surprised how often this concept is used. So the idea is that in this model, you have a probe and a response, and something emerges in there. And this emergence are fictitious particles. Now, at the beginning, you say, well, you're working with fictitious particles, you're not a serious scholar, and so forth. But it turns out that it's an important approach. For example, you're all familiar with the concept of a hole. And there are many engineers in Silicon Valley who spend their whole lives working on semiconductor devices, and they work on what an electron in a hole is. Now, the reason for the construction of a hole is that if you have 10 to the 23rd electrons, take out one, and you have to tell how all the 10 to the 23rd have behaved from taking out one, it's really a hard problem. But if you think of this in terms of that there's an electron absent and has a positive charge from the remainder, and you can think about how the hole moves, you're perfectly comfortable with that concept, even though, because it explains everything that you're observing, even though you can't have a beam of holes going across a room like this in principle. It doesn't seem like a real particle, but it does explain the properties. So it acts like a positive electron. And it's not like a Dirac positron, because those you can make. So it's really a concept in this sense. The other thing is when if you do an acoustic problem and you hit this thing with a hammer like I showed, and you talk about what's going on, you can say, well, there's sound waves in there because the ions are vibrating. But just like you can say, you can think of light as a particle or a wave, you can think of these vibrations as a particle, and you make a phonon. And so we use concepts of phonons and holes in everyday life as a condensed matter physicist, and yet these are mental constructions that explain responses. And so that takes you to the philosophy of Bergson, which was emergence. He said everything we sense are images. So since that's all we can deal with, the different ways of explaining it is something else. It's how you construct it. And I like telling about Bergson because he was a Frenchman. And at the beginning, he was a mathematician, young mathematician, and did some evidently very good work. I asked math colleagues but there was not a lot. But his thesis got published and so forth. And then I guess he was thinking of moving into physics. And he got into an argument with Einstein. He really didn't believe relativity at the beginning. And then I guess, to make a long story short, Einstein convinced him, and he was a big proponent. But there's still people who are wondering about some of the questions he brought up about the concept of time, which is important in Einstein's theory. And Bergson then moved into the philosophy of science, and there's some nice articles about the discussions between Bergson and Einstein. And then he got a Nobel Prize in Literature. So he was quite an amazing person. And the philosophy of science is something that when I was a student, if anybody mentioned it, they just walk out of the room, nobody wanted to talk about it. But because a lot of the philosophers that were doing philosophy of science didn't know a lot of science. But if you talk to some of the people nowadays, they're really schooled on details of quantum mechanics and so forth, and they worry about these things, and they worry about these concepts of emergence. Because, let's say in some fields, you talk about the emergence of space-time, and what is fundamental? In fact, I spent a lot of last week or a week and a half ago discussing these things with Michael Berry, who is quite interested in also working on these kinds of, thinking about these kinds of things. The question is what you can say that's going to be helpful. But I wanted to bring this up because even Einstein had a stage where he thought about things this way. When he did his photoelectric effect, he called it a heuristic model. And a heuristic model means a sort of an empirical model. And that's why I made a big thing about being empirical sometimes. We certainly want the students to be able to calculate. We want them to be able to compute. But we also want them to be able to sort of make little models and, what's really going on, and try to get not only a physical picture, but some kind of basic picture that explains the physics. So the feeling was that it was more of an emergent approach. And over the years, you of course did a lot that depended on reductionism. So with emergence, you explain properties in condensed matter physics in terms of elementary excitations and new states of matter. And so things like superconductivity is emergent property, magnetism, the quantum Hall effect, topological insulators. And you want these emergent phenomena, for example, to be stable. And so if you can find a topology example, like you can easily turn mathematically a coffee cup into a donut, but you can't turn it into a bowl. And as you all know, you can have a Mobius strip, which you can't turn into a single strip. So these are stable states. You want these emergent states to be robust. So in the topological insulators nowadays, we have these two-dimensional topological insulators that have helical edge states, no magnetic field, or in the quantum Hall effect, in the fractional quantum Hall effect, you have very stable phenomena. And these are stable because you reach a robust state, and you say that these states emerge. Well, superconductivity is a state of this kind. And if you look back at the original 1911 work of Kamerlingh-Onnes, where the resistivity as a function of temperature was coming down and then dropped to zero, you realize you're in a new state of matter. And this state of matter is stable. And if you get a persistent current in a loop and keep it cold, and you estimate how long it will exist, it'll go on for the age of the universe. I mean, numbers are very long. So in terms of semiconductors' optical properties, it was possible to take the optical properties, get the electronic structure, and actually predict that these materials, if they were doped, would be superconducting, and they were found to be superconducting. And later, just to finish up the kind of calculations you can do, you could take silicon and look at it under pressure, and it'll go into these phases. And germanium is a superconductor now too, gallium arsenide, and you can predict now superconductivity. So starting from these optical studies, you can get structural studies. You can get things like silicon at high pressures. And here's another one of those pictures where the total energy, there's diamond, and then you could show that silicon could go into these structures. They would be metals, they would be superconducting, and these were materials that were not known. But you could predict their existence, stability, lattice constants, mechanical properties, electron phonon properties, and this is and then the only input was the atomic number and the atomic mass because you're doing the phonons, and an estimate based on standard theory of the Coulomb repulsion. So silicon is, I like to say, maybe the best understood superconductor. It doesn't tell us about the new iron superconductors or the new copper oxide superconductors, but within BCS theory, you can do calculations using these theories. So our standard model of solids is interacting atoms and elementary excitations, and that's why, as I showed you, topological insulators and quantum Hall effect, these involve these other ideas. And so we use reductionism and emergent behavior. And so now theorists can explain and predict ground and excited state properties in many condensed matter systems, and they can make decisions about interesting things to do, but they never make the decision on what's right. That's always made by experimentalists. And unfortunately, up to now, all the major discoveries are made by experimentalists. But maybe in the future we can get a little further. So my conclusion is that many of the most important advances in the theory of condensed matter physics were made possible because of the study of optical properties. And when I teach condensed matter physics, I always say that in our field, and maybe all fields of physics, more fundamental physics has been learned by using photons than any other probe. And that you have to know about this. And so that's it. Thank you very much.
Okay, thank you very much. If there are any questions, I'm sure Professor Cohen is very eager to try to answer them. Yes, here.
Marvin, has the study of optical properties help us understand the defects in solids?
The defects? I think a lot, in the early days, there was certainly a lot of research using optical properties to look at the energy levels near a defect. And that had a big impact, particularly on semiconductor physics. Now, are you thinking of semiconductors? Yeah, and so, for example, Lottinger and Cohen did a lot of the theory of some of these defects, and the problem is that the early work, people did a lot of hydrogen-like approximations. So you basically made a hydrogen atom with a dielectric constant and an effective mass, and that gave you the properties of the defects. But when you get close to the core or get close to the defect, things get complicated. Nowadays, people are doing a lot more. Now, the problem with the studies in, let's say, the 70s was that the density functional theory was not giving you the right band gap. So you really weren't getting good enough values for the transitions. But now they're much better. So, yeah.
Marvin, I asked the same question in the taxi, but I'll ask in public. That it seems to me right now it is known that gallium nitride, LED, works very well. And it's full of defects. Now, there's something that works so well, everybody using it, there must be a model that could be at least indicate why that is the case. Just wanted to hear you without the taxi running around.
I don't know the latest research on this. So I don't know if people have come up with an idea that has been tested by the community. The point is that here you're making a lot of defects. So why would, let's say, an exciton be able to make it through the system? Now, first of all, one thing that's unusual about gallium nitride is, again, it's what I said about diamond. Nitrogen has no p states in the core. So gallium nitride is very different from gallium phosphide or gallium arsenide or the other 3,5 materials. So the ionicity is very different. So the scattering could be different. But an idea that I had that might convince you is the following. If you take a superconductor and you want to make Cooper pairs, all right? So you spin up, spin down, you make Cooper pairs. You take a K state with a spin down, K state, spin up, positive K, negative K, and you try to pair them. And then they go through and they give you superconductivity. Now you can really dirty up a superconductor and destroy that K, that momentum state as being a good quantum state, and it still works fine. And the reason is that the fundamental point is not that you have to pair K up with K down, but you have to pair time reverse states. So what you do is you take an energy state and average over all states around the Fermi surface, and you make up one state. And then you take another energy state and average all over, so you scatter first. So you think of it this way. Your Hamiltonian has a kinetic energy, and then it would have the pairing energy. But now it has a kinetic energy, and it has a dirt energy, and then it has a pairing energy. So the zero order state has the dirt in it, and the eigenstates are those energy states. They're not eigenstates of momentum. They're eigenstates of energy. And then you pair spin up, spin down. And that would be my interpretation of Anderson's theory of dirty superconductors, where he wrote a very cryptic paper that's referred to, but very few people read it or understand it. But I think that's what's going on. Now here, if the electrons are scattered around and the holes are scattered around, it may not be that it's a certain K state involved with another K state, but it could be an energy window. And if it's an energy window, they already have the dirt built in. And then if you could combine those two states and have them move through the crystal, they might be able to move through the crystal without things happening. Now, Ron brought up the point that maybe it's that the states have to go around the impurity, and you have to put it in a different way. But I have not done a real calculation on this, but I think that may be part of it. And the scattering is going to be different because nitrogen, gallium nitride is different. But I should give it to a student. It's such a hard problem, only a student can solve it.
Speaking of students, there are many students here.
Yeah.
And I invite you, once you tea or coffee, to ask a question. Please.
Yeah, okay. Today you're a student.
Yeah. Your question is about this double density hump between carbon bond, right? Actually, you mentioned it's somehow related to pi bond, but actually for this diamond, there's no pi bond, right? So
I didn't say pi bond.
yeah. So what is the implication for these double humps between the carbon
Oh,
atoms?
what happens is, let me do silicon first. I have silicon, okay? And then I have 4 valence electrons, and these are S2, P2, right? Now, so the S electrons, when they come near the core, they get pushed into the bond because there's a repulsive S in the bond. When the P electrons come near the bond, there's a P in the bond, pushes it out. Now, carbon, you have the core is just 1 S2, and then you have 2 S2, 2 P2. So the S electrons go into the bond, but the P electrons, okay, and not pi, the P electrons stay at their atomic position because they're just like there's nothing in there to really push them out, so they stay at the atomic position. So when they come together, they stay there, and then the charge has a double hump. And the double hump is there in diamond and in graphene or graphite.
Well, I think they do have a pi bond.
Yeah.
So
But then you have the pi bond. But then because of different geometry, you got you know, you got the state sticking out in the other direction. But here it just hybridizes it different. So if you wanted to do the same thing for silicon and you wanted the p states to stay there, you'd have to pull on silicon with a minus 85 GPa. And if you could do that, you can always push, but you can't pull. If you could do that, then it'll split the bond and you'll have two humps.
How do you understand silicene if they grow on metal surface?
How do you understand?
They're growing silicene on metal surface.
Oh, yeah. If you've got something else to hold it.
So
Yeah.
that's how they're doing it.
Right. If you've got something that can hold it, then you can mimic that. Okay.
Another question is between the metallic carbon nanotube and the semiconductor carbon nanotube have a junction. It's that the semiconductor nanotube is it's N-type or P-type. Normally you have a junction, you have a...
Oh, you have to dope it. I mean, basically, it just comes out with a gap. In other words, if you have the metal nanotube just has carriers at the Fermi level. The semiconductor just has the gap. But so this is a real semiconductor. It's not N-type or P-type. And then you put the Jockey barrier, just like taking pure silicon and pure aluminum. But you can dope it. Okay, students, any students?
I'm up with the student.
Yeah. Okay. No, you don't have any integrals you want me to do or anything? No. Okay, thank you.
Thank you very much, Professor Cohen. CP has a comment.